In this video, we introduce the derivative function. So we let f of x be a function. The derivative function which is denoted as f prime of x, or d dx of f of x, is the function whose domain consists of those values of x such that this limit exists. Function is said to be differentiable at a if f prime of a exists. More generally, it is said to be differentiable on S if it is differentiable at every point in the open set S. A differentiable function is one in which f prime of x exists on its domain. Now, an important property of differentiability is that it implies continuity. So we say let f of x be a function and let a be in its domain if f of x is differentiable at a and f is continuous at a. And the proof of this is really straightforward. So we say suppose that f of x is differentiable at a. What we have to show is the limit as x approaches a if f of x is equal to f of a. Right, that's what it means to be continuous. All right, so if we take a look, limit as x approaches a of f of x. We can write this as the limit as x approaches a of f of x minus f of a plus f of a. Right, so here all we're doing is we're adding by 0, and we are allowed to do that. Right? Adding by 0 does not change the value. We can now write this as the limit as x approaches a, f of x minus f of a divided by x minus a times x minus a, and then plus f of a. Right here, we multiplied this term by 1. Right? Multiplying a number by 1 does not change the value. This becomes the limit as x approaches a, f of x minus f of a all over x minus a times the limit as x approaches a of x minus a plus the limit as x approaches a of f of a. Right, this is the product rule of limits. This is the sum rule of limits. Now this piece right here is the derivative at a, because it is differentiable at a. Then that second limit is just 0, and that third limit is the limit of a constant, so it's just f of a. This is equal to f of a. That is what we set out to show, and so the proof is complete. So differentiability implies continuity. Is the converse true? That is, if a function is continuous at a, is it automatically differentiable at a? Well, in 3 of the examples at the end of this video, we are going to explore this idea. We now close out this video with several examples. So we want to evaluate this derivative. And what I typically do is I approach this in a 4-step fashion. The first 3 steps should be familiar if you remember from pre-calculus when we looked at the difference quotient. So the first step is to find f of x plus h. Now f of x was root x, so this is the square root of x plus h, and the idea is to try to fully simplify this. Well, that's already simplified, so we move on to step 2, which is take what we just found and subtract out an f of x. And again, you want to fully simplify this before moving on to step 3. Well, this is already fully simplified, so we move on. Take what we just found and divide out by h. If at all possible, we want to get rid of that h in the denominator. Well, to do that, notice we can multiply by the conjugate. Right, what we're doing here is we're actually rationalizing this fraction. But we're doing it differently. Normally, you'd rationalize it if you have a square root in the denominator. Here we want to rationalize it with the square root in the numerator because we want to try and get rid of that h. Now what we're going to be left with in the numerator is x plus h minus x In denominator, we'd be left with h times that square root of x plus h plus square root of x. That numerator can simplify to h all over that h times the sum. Now those h's drop out, and we are left with 1 over that sum. Now the fourth step is to take what we just found and take its limit as h goes to 0. So this is going to wind up being the limit as h goes to 0 of 1 over this sum, 1 over root x plus root x. So this is 1 over 2 root x. And this here is our derivative. So the derivative of square root of x is 1 over 2 root x. Next, let's go ahead and try and find the derivative of x squared minus 2x. So again, we attack this in a 4-step process. First, let's find f of x plus h. And simplify this as much as possible. So when you square, we'll be left with x squared plus 2xh plus h squared. Then we have that minus 2x minus 2h. I can get rid of these parentheses here. That is as simplified as it can be. However, we can rearrange some terms. I will not do that, though. I will just leave it like that. Now take that and subtract out f of x. Right, the x squareds drop out, then minus 2x's drop out. So we are left with 2xh plus h squared minus 2h. Third step is to take that and then divide out by the h. So this is 2xh plus h squared minus 2h all over h. We can factor out an h from the numerator. And this leaves us with 2xh plus h minus 2. And finally, take that and plug it into the limit as h goes to 0. I'm sorry, this should not have been an h there. And we're left with 2x minus 2, so this is our derivative. Next up, let's go ahead, find f prime of 0 for f of x equals the absolute value of x. Now, recall that absolute value of x can be defined as a piecewise. It's x whenever x is greater than or equal to 0, negative x whenever x is less than 0. So f prime of 0 would be the limit as x approaches 0, f of x minus f of 0 all over x minus 0. This will leave us with the limit as x approaches 0 of absolute value of x over x. To evaluate this properly, we need to take the one-sideds. First, we look at the left-handed limit. This becomes the limit as x approaches 0 of negative x over x, and that is negative 1. Now we look at the right-handed limit. This is the limit of x over x, and that limit is 1. Notice that these two limits are not the same. So that means the limit itself does not exist, and therefore f prime of 0 does not exist. However, absolute value of x is continuous at 0. So the question I posed earlier, which was to say, does continuity imply differentiability? If a function is continuous at a point, does that mean it's automatically differentiable at that point? The answer is no. If we take a look at this graph, so the absolute value function looks something like that. Notice here at 0, we have what is known as a cusp. Right? It's meeting at a point, at a pointed edge. So if you have a graph of a function, anywhere you see a cusp on it, it's not differentiable at that point. Let's now look at finding f prime of 0 for the cube root of x. Now again, f prime of 0 is the limit as x approaches 0 of f of x minus f of 0 all over x minus 0. This leaves us with the cube root of x, limit of the cube root of x over x, which can be simplified as x 1 over x to the 2/3. Left-handed limit is positive infinity, right? The right-handed limit positive infinity. So the limit at 0 is infinity. This means that f prime of 0 is infinite, so it does not exist. Now, if we look at what a cube root looks like, so the cube root is going to do something like this. And right at this point, the origin, if we are to zoom into it, what we would notice is right at that point, it is vertical. So whenever at a point it is the graph is completely vertical, the derivative does not exist, right? It's an infinite slope. It's an infinite derivative. But once again, cube root of x is continuous at 0. One last example. Right, we want to find f prime of 0 for this function. F prime of 0, limit as x approaches 0 of f of x minus f of 0 all over x minus 0. Now the reason that we take this as f of x is because if x is approaching 0, then x is not equal to 0. So this is now just the limit as x approaches 0, x sine of 1 over x all over x, limit as x approaches 0, sine of 1 over x. Now, if we look at this, as x approaches 0, 1 over x is going to either go to positive infinity or negative infinity, right? Depending on what side we're coming in from. Well, sine is just going to keep oscillating back and forth between plus and minus 1. This limit does not exist. So f prime of 0 does not exist. And I will not even attempt to draw what this function looks like. If you're interested, you can Google it. You should easily be able to find the graph of sine of 1 over x. Now, that brings this video to a close. Starting with the next video, we are going to start to investigate ways to take the derivative of a function without having to plug it into this limit definition. Right, the examples we looked at today weren't that difficult to use the limit definition. However, there will be some functions where it can be extremely difficult. So we would like to be able to come up with shortcuts. And that is what we start with in the next video.